Logical classification of input devices. The various kinds of input data are summarized in the following 6 logical device classifications used by FIGS and GKS. Locator, a device for specifying coordinate position x, y. Stroke, a device for specifying a series of coordinate positions. String, a device for specifying text input. Valuator, a device for specifying scalar values. Choice, a device for selecting menu options. Pick, a device for selecting picture components. In some packages, a single logical device is used for both locator and stroke operations. Some other mechanisms, such as switch, can then be used to indicate whether one coordinate position or a stream of positions is to be input. Each of the 6 logical input device classifications can be implemented with any of the hardware devices, but some hardware devices are more convenient for certain kinds of data than others. A device that can be pointed at a screen position is more convenient for entering the coordinate data than a keyboard, for example. Locator devices. A standard method for interactive selection of a coordinate point is by positioning the screen cursor. We can do this with a mouse, joystick, trackball, spaceball, thumb wheels, dials, a digitizer stylus, or a hand cursor, or some other cursor positioning device. When the screen cursor is at the desired location, a button is activated to store the coordinates of that screen point. Keyboards can be used for locator input in several ways. A general-purpose keyboard usually has 4 cursor control keys that move the screen cursor up, down, left, and right. With an additional 4 keys, we can move the cursor diagonally as well. Rapid cursor movement is accomplished by holding down the selected cursor key. Alternatively, a joystick, joydisk, trackball, or thumb wheels can be mounted on the keyboard for relative cursor movement. As a last resort, we could actually type in coordinate values, but this is a slow process that also requires us to know exact coordinate values. Light pens have also been used to input coordinate positions, but some special implementation considerations are necessary. Since light pens operate by directing light emitted from the screen phosphors, some non-zero intensity level must be present at the coordinate position to be selected. With a raster system, we can paint a color background onto the screen. As long as no black areas are present, a light pen can be used to select any screen position. When it is not possible to eliminate all black areas in a display, such as on a vector system, for example, a light pen can be used as a locator by creating a small light pattern for the pen to detect. The pattern is moved around the screen until it finds the light pen. Stroke device. This class of logical devices is used to input a sequence of coordinate positions. Stroke device input is equivalent to multiple calls to a locator device. The set of input points is often used to display line sections. Many of the physical devices used for generating locator input can be used as stroke devices. Continuous movement of a mouse, trackball, joystick, or tablet hand cursor is translated into a series of input coordinate values. The graphics tablet is one of the more common stroke devices. Button activation can be used to place the tablet into continuous mode. As the cursor is moved across a tablet surface, a stream of coordinate values is generated. This process is used in paintbrush systems that allow artists to draw scenes on the screen and in engineering systems where layouts can be traced and digitized for storage. String devices. The primary physical device used for string input is a keyboard. Input character strings are typically used for picture or graph labels. Other physical devices can be used for generating character patterns in a text writing mode. For this input, individual characters are drawn on the screen with a stroke or locator type device. A pattern recognition program then interprets the characters using a stored dictionary of predefined patterns. Valuator devices. This logical class of devices is employed in graphics systems to input scalar values. Valuators are used for setting various graphics parameters such as rotation angle and scale factors, and for setting physical parameters associated with a particular application, temperature settings, voltage levels, stress factors, etc. A typical physical device is used to provide valuator input in a set of control dials. Floating point numbers within any predefined range are input by rotating the dials. Dial rotations in one direction increases the numeric input value, and opposite rotations decrease the numeric value. Rotary potentiometers convert dial rotation into a corresponding voltage. This voltage is then translated into a real number within a defined scalar range, such as -10.5 to 25.5. Instead of dials, slide potentiometers are sometimes used to convert linear movements into scalar values. Any keyboard with a set of numeric keys can be used as a valuator device. A user simply types the numbers directly in floating point format, although this is a slower method than using dials or slide potentiometers. Joysticks, trackballs, tablets, and other interactive devices can be adapted for valuator input by interpreting pressure or movement of the device relative to the scalar range. For one direction of movement, say left to right, increasing scalar values can be input. Movement in the opposite direction decreases the scalar input value. Another technique for providing valuator input is to display sliders, buttons, rotating scales, and menus on the video monitor. This figure illustrates some possibilities for scale representations. Locator input from a mouse, joystick, spaceball, or other device is used to select a coordinate position on the display, and the screen coordinate position is then converted to a numeric input value. As a feedback mechanism for the user, the selected position on scale can be marked with some symbol. Numeric values may also be echoed somewhere on the screen to confirm the selections. Choice devices. Graphics packages use menus to select programming options, parameter values, and object shapes to be used in constructing a picture. See figure. A choice device is defined as one that enters a selection from a list menu of alternatives. Commonly used choice devices are a set of buttons, a cursor positioning device such as a mouse, trackball, or keyboard cursor keys, and a touch panel. A function keyboard or button box designed as a standalone unit is often used to enter menu selections. Usually, each button is programmable so that its function can be altered to suit different applications. Single-purpose buttons have fixed, predefined functions. Programmable function keys and fixed function buttons are often included with other standard keys on a keyboard. For screen selection of listed menu options, we can use cursor control devices. When a coordinate position x, y is selected, it is compared to the coordinate extents of each listed menu item. A menu item with vertical and horizontal boundaries at the coordinate values xmin, xmax, ymin, and ymax is selected if the input coordinates x, y satisfy the inequalities. X lies between xmin and xmax, y lies between ymin and ymax. For larger menus with a few options displayed at a time, a touch panel is commonly used. As with a cursor control device, such as a mouse, a selected screen position is compared to the area occupied by each menu choice. Alternate methods for choice input include keyboard and voice entry. A standard keyboard can be used to type in commands or menu options. For this method of choice input, some abbreviated format is useful. Menu listings can be numbered or given short identifying names. Similar codings can be used with voice input systems. Voice input is particularly useful when the number of options is small, 20 or less. PIC devices. Graphical object selection is a function of this logical class of devices. PIC devices are used to select parts of a scene that are to be transformed or edited in some way. Typical devices used for object selection are the same as those for menu selection, the cursor positioning devices. With a mouse or joystick, we can position the cursor over the primitives in a displayed structure and press the selection button. The position of the cursor is then recorded, and several levels of search may be necessary to locate the particular object, if any, that is to be selected. First, the cursor position is compared to the coordinate extents of the various structures in the scene. If the bounding rectangle of a structure contains the cursor coordinates, the picked structure has been identified. But if two or more structure areas contain the cursor coordinates, further checks are necessary. The coordinate extents of individual lines in each structure can be checked next. If the cursor coordinates are determined to be inside the coordinate extents of only one line, for example, we have identified the picked object. Otherwise, we need additional checks to determine the closest line to the cursor position. One way to find the closest line to the cursor position is to calculate the distances squared from the cursor coordinates x, y to each line segment whose bounding rectangle contains the cursor position. See figure. For a line with endpoints x1, y1 and x2, y2, distance squared from x, y to the line is calculated as d squared equals delta x into y minus y1 minus delta y into x minus x1 the whole squared over delta x squared plus delta y squared, where delta x equals x2 minus x1 and delta y equals y2 minus y1. Various approximations can be used to speed up this distance calculation, or other identification schemes can be used. Another method for finding the closest line to the cursor position is to specify the size of a pick window. The cursor coordinates are centered on this window, and the candidate lines are clipped to the window as shown in this figure. By making the pick window small enough, we can ensure that a single line will cross the window. A method for avoiding the calculation of pick distances or window clipping intersections is to highlight the candidate structures and allow the user to resolve the pick ambiguity. One way to do this is to highlight the structures that overlap the cursor position one by one. The user then signals when the desired structure is highlighted. An alternative to cursor positioning is to use button input to highlight successive structures. A second button is used to stop the process when the desired structures is highlighted. If very many structures are to be searched in this way, the process can be speeded up and an additional button is used to help identify the structure. The first button can initiate a rapid successive highlighting of structures. A second button can again be used to stop the process, and a third button can be used to back up more slowly if the desired structure passed before the operator pressed the stop button. Finally, we could use the keyboard to type in structure names. This is a straightforward but less interactive pick selection method. Descriptive names can be used to help the user in the pick process, but the method has several drawbacks. It is generally slower than interactive picking on the screen, and a user will probably need prompts to remember the various structure names. In addition, picking structure subparts from the keyboard can be more difficult than picking the subparts on the screen.